What's up, you guys? This is Peter again, and this time I want to go over one of my favorite nodes in Houdini. Spoiler, it's the shortest path node. So let's dig into Houdini and show you what I mean. I'm gonna adjust over here the webcam thingy again, and let's dive inside. So I need some geometry to start working with. So I'm going to create the test geometry, the rubbertoy, aka Flippy. So with this toy, we can basically dive inside and have a quick look. Now this geometry is not closed geometry, and that is going to become important later on when we have our cost attribute that will need to be calculated. So one of the things we can do with this is turn this into one continuous geometry. I'm going to turn this into a VDB. So we can say VDB from polygon, and that will turn it into one watertight mesh eventually. So currently I'm trying to compute the VDB volume over here. I can give it a little bit more detail. That's good enough. And then we can say convert VDB back to polygons. Convert VDB back to polygons. Now we could make this adaptive if we needed to, right? Now this resolution is maybe too low, so let's give it a little bit more. All right, so this is better. We have a lot of resolution now, and we are dealing with polygons again. Now, right now, I don't want to change the adaptivity. I could sort of start, changing the mesh over here, the topology, but I don't want to do that because I want to have a fairly uniform topology. We could even remesh it so that we sort of go to a more triangulated mesh, and that could perhaps even be a better, a better approximation. So right now I've got a fairly clean, even topology, and that's going to be important. So the next step that I want to do is I want to select one point, and then that is going to become our root point. So we can simply go in, select a point, maybe on a tip over here, we can select one or multiple points, and I'm going to group that. So we make a new group, and I'm going to call that group roots. Roots. So the next thing that I want to do is indeed drop down that shortest path, find shortest path. And so this node, find shortest path, basically allows you to calculate either direct paths with a start and end point, but another way that you can use it is over here with that cost attribute. So right now it's kind of complaining because it doesn't have any endpoints. We want to give it the group roots as the start point, and the endpoints we're basically going to ignore because all the points are going to become endpoints. So from each start to any end, I'm going to say any start to any end. Calculate the cost attribute. So let's have a look. What does that look like? Right now, if we evaluate this, oh, no endpoints. I don't need any endpoints. I don't need any paths. So if you turn off the paths, then it will simply compute the cost attribute as is. Okay, so with this, what has this thing generated? Well, there is an attribute now called cost, and this is really what we're after. So let's have a quick look. If we look in the spreadsheet, then we can see what this cost attribute actually does. So it's got some values on it, and if we kind of sort by these values, you can kind of see, here, cost 0, and this point number 1245. Well, which one would that be? Well, basically it is going to be the one over here that is sitting right at the edge, right at the end, the one that we basically selected as a root. So what does this cost mean? Well, this is basically the cost that it takes to traverse the mesh. So that means how much does it cost in terms of distance, in terms of length, to travel from, say, point 1245 to point 517. Well, there's going to be a certain, cost associated with that. And then, every additional point, let's say 515, right, is going to accumulate that cost value. So the first segment we might want to sort of compute is this one. The next one is going to be, this one, and so on. And so basically this first segment is going to add to the second segment, and it's going to store the cost value there. So what we're going to end up with is this entire gradient that is covering the entire mesh. Well, that is if the mesh is connected. I can show you what would happen if the mesh is not connected as well. Then it will basically give you a debug value of -1. But for now, let's visualize these cost values. So the main thing that I want to do before visualizing is there will be a minimum cost of 0. That's where the roots are, and a maximum cost as well. which is probably going to be, I don't know, somewhere the furthest away from the root. So maybe all the way over here, or maybe it's one of these. I don't know, but we will be able to visualize that, and then we can see it. So the first thing I want to do is normalize that attribute. So one thing I want to do is attribute promote that cost attribute, and then we can promote it to the detail level and say we want the maximum of this cost. And it's probably a good idea as well to rename this to something along the lines of cost max. So now I've got two attributes. I've got cost, the current value of the point, and then on the detail attribute, I've got cost max. So next I want to do the normalization, and we can do this quickly in an attribute fob so that we can also visualize the attribute. So here we'll call this one cost normalized. And let's dive inside. I'm going to bring in the cost attribute with a bind node, cost, and simply remap it with a fit function, fit range. The current value, the source min, is going to start at 0, and source max is going to be that maximum. So we can use a detail attribute for that, import detail attribute, and the attribute that I want is going to be called cost max, cost max. Now, which geometry? It is going to be from the current geometry, so that is ourselves, the attribute we already have, and the result is over here going to be fed into source max. That's that cost max attribute. Okay, let's have a quick look. Let's visualize that. So if we now feed this into the color channel, then we will be able to see it as a gradient in our viewport. So here it's black. That means the values of the cost are close to 0. It's kind of like a percentage, right? So we basically are now able to visualize this as a percentage. Just like last time, if you watched the other tutorial, we can use a rainbow ramp to also visualize the ranges a little bit better. I like this particularly because this gives me quite a nice sort of, gradient rather than just black and white. So we can kind of see how this cost attribute is kind of nicely spreading out over this mesh. The next step is we can do something with this, because ultimately this gradient, well, it's kind of nice to see by itself, but ultimately we want to do something with this. So a good idea is to export that normalized cost, because I'm going to store this in a new attribute called cost and normalized cost. And so now we can kind of feed this into a variety of different functions. So one of the things I might want to do is try to see if I can run a shockwave through this object. And we can do that in the shader, we can do that in the displacement. Right now I just want to do that inside of the sub context. So over here, I want to sort of cost absolute deform. So we can use the normals, deform with an M. We can use the normals to deform the object, or initially let's just map color to it so we can see it as well. But notice that I'm mapping over here cost absolute. So what does that mean? Well, again, we have cost normalized. So cost normalized means that the cost value goes between 0 and 1. Now, cost absolute brings that normalized value back into our scene. So currently I want to map this cost attribute to the time, so to the frame numbers. So we can basically say start at frame 1 and end at frame 100. So if we were to say fit, a little fit range over here, and grab that normalized cost attribute, we already know that the min and max range is 0 to 1, and so the output range, the destination min and max, that is what we want to give the user some control over. So my destination min and max over here, we're going to grab both of these, and let's set the minimum to 1, and maybe set the entire range to 100 frames, that's 4 seconds-ish. And so the end frame, the destination max over here, we can set to 100. And so now, again, if we wanted to, we could say bind export this result into cost absolute. Okay, so that's going to be useful to keep track of with the cost absolute. So let's have a quick look at the attributes. In the spreadsheet, if we look at the spreadsheet, we now have multiple variations of cost. We have cost as is, as we computed it. Then we have cost normalized, the percentage representation between 0 and 1. And then we have cost absolute, which is basically going to be the temporal representation. So every point will have almost like a start frame or a trigger frame that is going to be between 0, or in my case 1, and the final frame. So now if we look at it, we can see over here cost, right? And if we sort by cost. We can see 0. We have cost normalized, right? So that's going to be our normalized cost between 0 and 1. And then finally cost absolute, which is some variation of that cost map between 1 and all the way over here to 100 at the final cost value. So what can we do with this now? Well, if we say we can either do the deform in one node, or if you like, we can split it out and again, another attribute VOP, so that it drives different things. So maybe we'll keep the deform separate so we can do something with it. Now I just checked if I already had a facet sub so that I can do something with the normals later for deformation, so we can do that in just a moment. But let's first visualize what that wave of deformation is going to look like. So let's bring in with a bind node over here that cost, but this time the absolute value, absolute cost, absolute. And so I want to remap it between 0 to 1, but with some duration in there. So if I set a fit function again, and this time I'm going to drive it, instead of it cost absolute, we're going to use the frame value over here and drive it. So the minimum cost value is going to be source min. Now what is source max going to be? It is basically that cost absolute plus somewhat of a duration. So we can kind of see if we add a little bit of value to this cost absolute, let's say we're dealing with time, right? So we can basically say 10 frames. We can create a new parameter here and say we'll set it to our offset or duration again. And let's say 10 frames all the way up to maybe even 100 frames if we wanted to, offset it more. So this is going to go into source max, and that value is going to be mapped between 0 and 1. So if we now run that value into the color, we will basically see a gradient travel through our mesh. So there we go. So basically it goes a little quick, but it is basically triggering something, right? So over here it becomes a white, and notice the way that it does it. It is traveling along the mesh. It is nicely spreading out. It is not so much a radial point that spreads out. Instead, it traverses the mesh, and that is crucial with this because basically that gives you very nice growth patterns. So if we now do something with this pattern, we can either make it go back down as well. So this would be our ramp where it goes up, and we can also have another ramp where it goes back down. So an easy way of doing that is feed this through a ramp where we can kind of control the outline of our leading edge. So we already know that our maximum duration is 10 frames. That is going to be mapped between 0 and 1, and then the 0 and 1 output over here is being mapped into the input of the ramp. Now lastly, I like using spline ramps, and so we can basically modify this over here. Let's say initially it is at 0, then it is going to ramp up pretty quickly. Also, maybe not a bad idea is to give this a nice smooth ramp. So I like using B-splines because they give me nice interpolation. So here B-spline, the last point as well, go make that into a B-spline. And then let's have this ramp down, and this can also go to 0, value go to 0. And maybe let's put in another point so that at least it is going to be bright for a while before it sort of falls off. So a nice sort of shockwave profile that we have here that is being fed into our curve. So now if we look at this, right, I can basically see, okay, the ramp over here, where did my ramp go? Well, because we defined it inside of VOPs as a default, it hasn't necessarily, been taken over here. So we can simply right click on this and say revert to defaults, and that is going to provide us our ramp. And immediately you can kind of see that over here, that ramp profile is being used. So if you look through it, we have a shockwave that travels through our system. So that's a lot of fun because now you can do all kinds of fun little experiments with this. So we could drive a deformation with this. I have calculated here, pre-computed some normals on the mesh. So what if we were to bulge this outwards, like a ripple that it travels through the system? Well, that's simply going to be a displacement, and I'll leave the color here so we can see that as well. That's simply going to be a displacement. So if we say something along the lines of displace along normal, we can grab our point position on the one hand, then we can also grab our normal and feed it in here and displace it along this point. Now notice I have an amount and a scale, and I want to use that over here, this amount that is coming out of my ramp, to drive now the amount of displacement. So let's have a quick look. it's way too strong. So we might want to multiply the scale down. And one of the things we can have here, they already have a multiplier there. It's the scale parameter. So we might as well, hook that up over here with the scale value. So here, let's set that to a default of something small, maybe 0.05, something like this. And then lastly, we can also change that duration so that our ramp basically falls off a little bit slower. So here, instead of 10 frames, we can double that or triple that, 30 frames, and now my ramp is going to fall off a little slower. So that's cool. And then let's also maybe promote that value, that scale value, we have it over here. So now we can have a ripple travel through, right, the entire sort of trajectory. And you can do all kinds of fun stuff with this. You can use this to emit particles. You can use this to control the p-scale of some objects that are scattered onto this, but overall a very fun little effect. So with that, that's kind of what I wanted to cover. We can also post multiply this with some noise or subdivide, but overall this cost attribute is pretty powerful. Actually, one more thing that is pretty nice to potentially cover is what if we wanted to have it less uniform, because right now it's kind of uniformly traveling over that object. And so what we can do is artificially say that the incoming geometry to the find shortest path, right, has certain areas of higher resistance and lower resistance. And so if we select the find shortest path, under the path cost, there is another option here, point cost attribute. And what we can do is we can define a little bit of a noise pattern, right? So let's build a quick little noise pattern over here. And we're going to say this is going to be, I'll call this a resistance attribute, resistance. So that means some areas of the mesh are going to be easier to traverse and others are going to be harder. Think of it like traveling, all these, this cost is traveling either over ice or over sand. It's going to slide much quicker over ice than it does over sand. So it's going to, require more energy, or it's going to be more expensive to travel over, high cost areas. So let's create a quick little turbulent noise here, and we can feed that into our own custom attribute. So turbulent noise, let's grab the position. Also a quick little note, if we right click over here, Vex options, we can simply say create input parameters, and that is going to create all of our input parameters very quickly rather than manually go through and set all of them. Now these noises have different ranges depending on what it is. In the help file you can kind of see the different ranges. I personally like the sparse convolution noise a lot. The alligator noise is also not bad. It's the default noise that goes between a range of 0 to 0.5. Now the sparse convolution noise over here goes between a range of about -1.7 to +1.7. Now I've used these noises a lot, so I kind of know these values somewhat by heart, but there's good information in the help file. So if you simply go up, select the node and go to the help file, you would learn more about these ranges. I'm going to fit this -1.7 to +1.7, so that is nicely remapped again, that normalization between 0 and 1. So you kind of see that normalization of attributes is really important. Okay, so now we can see it in the viewport. It's not quite what I want. Also, we might want to crank the contrast a little bit. So what if we say -0.3 to +0.3? So now we can kind of see there's more contrast into our noise, and we can change the frequency a little bit too. So let's go with a little bit of higher frequency here, right? So this will give me islands of strength, right? So certain areas are like pretty slow to traverse, and others will go much quicker. So then the next thing that I want to do with this is I want to export this, export this into a resistance attribute. And it's going to be a single float attribute. We can leave the color in there as well if we wanted to, resistance. And the only reason why I call it that way, you can call it Bob or you can call it whatever you want, but it sort of makes sense in terms of like resistance to travel the mesh. And I like to give my attributes either names that are common within Houdini or names that are making sense to me what it does. So we're going to use that resistance attribute now over here as a point cost attribute. So when I put in resistance, if I can spell it correctly, there we go, resistance, then the shortest path is going to recompute itself, and it's already done it, it's that quick. And so now if we look at our shockwave as it travels through, right? We can basically look at it from the deformation. Then you kind of hopefully see that it is no longer, you know, that even uniform wave that we had before. So if I were to temporarily disable that, we're going to be able to see the difference. So disable that, it's a nice and clean shock wave, and then re-enable that, and we basically have a lot of breakup. So let's play this back and let's have a quick look how that, you know, attribute transfers. So there we go. Yeah, so it's a shock wave and it covers everything, but notice that there were some areas, especially sort of over here, that took a lot longer, right? Or I guess maybe it's the other side, that took longer to go over. So some areas like here, it grows really quickly. And so if we look at this area here that is growing really quickly, why is it growing so quickly? Because we'll see that the resistance over here is going to be close to 0. So if we scroll back up and we go back to this resistance attribute, you'll see a big black patch, right? And so anything that is white is going to be slow to traverse. Anything that is black is going to be fast to traverse. And then we've got the in-between grayscale values as well. So this is particularly nice if you wanted to say, you know what, I want to have this you know, fin, for whatever reason, grow really slowly. So one of the things we could do is create a quick little point in there, add this point, and then we can do a color attribute transfer. So if I were to say, you know, actually even better than a point, let's use a primitive sphere, because a primitive sphere has a point on the inside, but then we can also see it in the viewport. It's a little bit easier to sort of, you know, debug what we're doing. So I'm going to append a transform, right? And then move that point so that it sits somewhat close to that flipper, right? So here to that area. It doesn't need to be too exact, sort of somewhat in the vicinity is fine. And I'm going to give it a nice pink color. So we'll talk a bit about later. You'll see why I do this sort of pink color. Really what we care about is the red channel. And what I want to do next is attribute transfer onto my geometry. Here onto my, before we do the resistance or even after the resistance, we don't really care. We can basically set the entire color value to simply be blue. And so when we attribute transfer, I'm going to create a nice fall off region nearby that flipper, and that area is going to simply start growing a lot slower. So the attribute that I want to transfer is the color attribute, CD, diffuse color. And we can kind of say, okay, go and make a nice soft fall off, right? So something along these lines, if we kind of look at it. Maybe let's move it so it sits a little closer to this side of the flipper, right? So something like this. This is good. So this will allow me to control which areas of my shock wave are going to travel faster and which are going to be slower. So if I were to say add this color value to the existing resistance attribute, remember our resistance attribute is 0 to 1. And here, if you were to see, well, think about the red values. That's also a gradient that goes between 0 and 1. So we can simply go and grab the color value and add it to the color value over here from the second input and add it to the existing resistance. So if we were to say go bring in that resistance attribute, bind export eventually resistance, and we are also going to grab the color value from the second input and add these two together. So from the second input, up input 2, grab that, grab the point number. The point numbers are the same, so we can just hook them up. The color value is correct. It is a vector 3. And then simply let's extract out the red component from our color here, red component value, and add it to the existing resistance. So we can say add that to there. Now, if we really wanted to, we could put a multiplier in here, kind of a weighting operation, like as in not waiting for the bus, but weighted, like a weighted average. So it's a little bit different. So, okay, let's see. Now, next I want to export this, bind export. And if we were to feed this now into the color value, then we're going to have values that are higher than 1. So we'll see that this flipper is going to be, let's do resistance. We're going to see that this flipper is going to be super bright. So it's going to be over here, super white, right? Whereas the other portions of the Flippy are going to be sort of grayscale or black. So that means this is going to be really expensive to reverse. So if we kind of, push this into our find shortest path, all that we've done is over here, add resistance to flipper, right? so we can kind of control it. So let's loop through the rest of it, the normalization, cost absolute deform, all that kind of stuff. And then here, attribute deform. So maybe for right now, we can kind of sort of see as it loops through it, and the flipper is probably going to resolve itself last. Notice how slow it's going, right? And then finally, it has resolved itself. And so with that, I think it's quite a fun little effect. And you can do lots of fun, gradient, sort of gradient-based, operations with this. So I think the most important part is this cost attribute and to understand what it does. Underneath here, this node can do so much more, right, than what I've just covered. It can, do arrays of costs and things like that. But we'll get into that maybe in a later stage. But the main thing is if you set it from any start to any end, so that's the crucial part here, and also don't output any paths. We want the cost attribute. Other things that it can do, which is also super useful, is, for instance, grab the previous point, the start point, those kind of things. And here the resistance attribute if we want to modulate that cost as it traverses the mesh. Okay, so that's kind of what I wanted to cover today. So hopefully you've learned something again, and with that, I would say if you like these kind of videos, please like and subscribe. Thank you, and see you in the next video. Bye.